our processes of change of heat and then exchanges of heat due to change of temperature, high conduction, body contact, convection move from place to place, advection horizontal, and then radiation via the space. Now we go into adiabatic process, and with all this previous discussion is diabatic process. Now the adiabatic process, which is expanding compression of air particles. Warmer air rises, forming cloud. Then cold, moist air, because the higher it goes, the cooler it becomes. But the warm one is very close to the surface, the earth surface. The wind now is the wind that carries it up and down. Therefore, an adiabatic process is one in which no heat is gained or lost by the system. But if you refer back to our first law of thermodynamics, that implies that it means that the heat energy for an adiabatic process is equal to 0. We said no heat is gained or lost. Make it different from the previous discussion of diabatic process. So that means all the change in the internal energy is in the form of the work done by the gas. This type of situation, which we call adiabatic process. That's the definition for adiabatic process. So if a material changes state, that is pressure, volume, or temperature, without heat applied to it, no heat is being applied to it, or added to it, or withdraw from it, that change is said to be adiabatic. Adiabatic process, therefore, repeatedly occur when air rises or descends as an important process in the atmosphere. When it rises and when it descends. Now, all this talk, grammar, we put it in form of mathematics. But mathematical equation. So, the work done, which we have known from the first law of the work done is the volume that is changing. Don't forget, PTF. The volume changes from initial to final. And then, for adiabatic condition to take place, it means that this must be constant. Because there is no heat applied. So, if this is constant, it's K. And the quantity of heat, which we said no heat is applied, means that it's equal to 0. And from the first law, if the quantity of heat equals to 0, it means that the change in internal energy must be negative of opposite of the work done on it. Don't forget our first law is the U equals the Q minus the W. So if that the Q equals 0, then it means that the internal energy is equal to the opposite of the work done by the gas. So this we already know. By the time we put the number of moles, the gas constant now become 3 over 2 into the change in temperature. Same as the internal energy, same as the minus work done on the gas. So the work done, therefore, will now be this over this NR into initial temperature minus the final temperature. So because the constant, we integrate, this is the constant from volume 1 to volume 2, and this one is the volume changes using volume, you must apply the constant K. But if you are using temperature, you use the gas constant and the number of mole of the gas. So by the time we integrate this one, heat is, and this is what we call, this is the adiabatic. The constant at adiabatic is the specific heat capacity at constant pressure divided by the specific heat capacity at constant volume, which is the ratio of the specific heats of the gas. It denoted as gamma or constant K. This is just to further expansion using the ideal gas law derivation, U equals Q plus this, all this. Just different ways of deriving when Q is equals to 0, the heat. This is what we have, minus from initial to final of the volume. If you know the volume, the number of mole, the gas constant, the volume, the change in volume. Assuming the heat capacity does not vary during the temperature interval, then we can use this equation. We can use this. The specific capacity at constant volume, then the temperature will be changing. This one, the volume change, and then at constant temperature. This one, the temperature change at constant volume. From T1 to T final, then inverse of T dt will give us this gas constant into V into that. So just manipulate the equation. We can now equate T final temperature divided by the initial temperature at either constant volume or constant pressure, and then the initial volume over the final volume, which is C is the constant volume divided by number of mole and then the gas constant. So this is laboratory experimental to verify all this, just the equation, the same equation I just when you have a gas inside a piston like that, and then you press, you allow it to either go down or go up, or without adding the heat. Then that means the change in the internal energy is equal to that of the work done on the gas, the work done. The opposite, which is going to be minus. So this one is equals to 0, this one becomes minus, and then when this one comes here, it becomes du plus the W. 0 du plus P dV. Just repeated of, but this is laboratory experiment of what we just discussed. We have related it to the atmosphere, related to how to can perform well. But this is not for your class anyway, for the engineering or physics course. So just to show them the same way, arriving at the same equation. Concerning this, note that air parcel expands as it rises from the surface to the atmosphere. As the elevation increases, the air pressure also decreases. This we already discussed in the first class, that we saw how pressure and temperature decrease with elevation. I already given you the graph in that slide. The molecule in the parcel of air uses their kinetic energy to expand the parcel of air. I have to skip this because you are not an engineering class. How we relate kinetic energy, which is half mv squared, into all these equations that, but don't need to bother yourself, but still have to make mention of that. Because when molecules move from point to point, is converting from initial G naught to Gf by potential to kinetic. We don't need to bother ourselves with the mathematical jargons. The temperature of the parcel of the air also decreases with elevation. Just say the elevation increases, the air pressure decreases. The elevation increases, the temperature also decreases. That's why we say the higher you go, the cooler it becomes over there. The molecules therefore lost their energy and then slow down their motions. The lost energy is used to increase the potential energy of the air molecules. In the same way, when the air parcel descends, the potential energy of the air molecule is converted back, because it's now moving, descending downward into kinetic energy, causing the air temperature to rise. If it is cooler over there, and then it's coming down, then what happens? The temperature will increase. When it is going up,